Okay. Good afternoon, everyone. My name is Pedro Fortuna. I am one of the founders of OWASP. I'm here to talk about JavaScript obfuscation, to address common myths and misconceptions around it. I'll start by talking about the main concepts behind obfuscation. Then I'll proceed to present some metrics to measure obfuscation quality. And finally, we'll go through a series of different examples. So one definition of obfuscation I like is the one from Colbert and Nagra, which defines obfuscation as transforming a program into a form that makes it more difficult for an adversary to understand or change the original code. And by more difficult, they meant requiring more human time, more money, or more computing power than to analyze the original program. But you can also define it as the process of lowering the code quality in terms of code readability. So you delay program understanding, hopefully to the point where the time needed to reverse it clearly exceeds the useful lifetime of the program, or the resources that you need to spend clearly outweighs the value that can be obtained from reversing that code. It also is the process of lowering the code quality in terms of maintainability. You delay program modification, and hopefully to the point where the costs of reversing successfully that program will be much higher than developing that code from scratch. A common misunderstanding around obfuscation is that some people think that it's like encryption, where in fact it's very different. In this example, you can see JavaScript source code which gets encrypted, and when it is in the encrypted form, it cannot be executed by the JavaScript engine. You must first pass this code through a symmetric decryption function. Only then you can execute it on the JavaScript engine. And here you can see that when you apply obfuscation to the source code, you get JavaScript, which is valid and ready to execute on a browser. So in this case, you don't need a symmetric function to convert back to an executable form. Now, before moving forward, let's look at an example. Here you can see a small function that writes that picture you see on the left. Now, being JavaScript, this code is delivered to the browser, so anyone can capture this code. And here you can see an obfuscated version of the same code. Anyone can still capture this code, but in this case it's much harder to read and understand this code. So what is it good for? You can use it to prevent a competitor from stealing and using your code as a quick start to make a similar product. You can protect intellectual property, hiding algorithms, hiding data like secret keys, or just hide watermarks in your software. You can enforce license agreements. The default case for JavaScript, you cannot enforce license agreements. But if you add additional code that can, for instance, check if the code is running on a certain domain, or to make the code expire after a certain date, you can achieve a certain level of license enforcement. You can also use it as an additional layer of security, because as it is more difficult to understand the code, one can argue that it's more difficult to spot vulnerabilities in that code. And you can also use it to test the strength of security controls such as IDS or OWASP. But on the evil side, you can also test the strength of the security controls, but not for fixing them. You can hide malicious code, or you can make code look like harmless code. Well, now, a common question that is often raised is, why not relying on the server? You can move security-sensitive code to the server, and whenever you need it, you make a request to the server. Now, most of the time you can do that, and in fact you should, but there are plenty of situations where you cannot do it, because, for instance, starting in situations where you don't have a server, or you are not allowed to use one. Some examples are widgets, mobile applications, standalone offline playable games, and Windows 8 applications developed using JavaScript. And there are other situations where you just don't want to, because you don't want to spread the resources that are needed to provide that service, because you have to have support teams, you have to guarantee uptime, so it's usually, it may not be convenient to you. And the other situation is the latency. Sometimes you need the data and you need it fast, so it's not viable to request that information from the server. You can imagine, for instance, a game which needs to calculate the next frames, and you cannot wait for a TCP connection to be set up and ask the information from the server. Now, moving on, you can measure the quality of obfuscation using some metrics. For instance, the obfuscation potency, resilience, stealthiness, execution cost, and maintainability. Now, the first one is the potency. You can look at it as the measure of confusion that gets added to the code by the obfuscation. Or if you prefer, is how hard it gets to understand the code by applying the obfuscation. On the left, you can see a simple example of a factorial function. And by applying the rename all obfuscation and also comments removal, you obtain a code where you can see the names of the functions and variables are replaced by a mix of lowercase and uppercase O's. In this case, well, everybody knows that the function names and variables, it really helps you understand what the code does. So in this case, not only you don't have that, but the names chosen to replace the original ones also introduce further confusion in the code. And also removing the comments does not help. So this form of the code, you may say that it's more potent in terms of obfuscation than the original code. Now, the third example is the application of white space removal to the second example. It becomes slightly harder to read, so we can say that it's more potent than the previous form. The second one is resilience. We can define that as the measure of resistance that the obfuscation offers to the obfuscation techniques. You can see the same code again. And by applying manual or automatic techniques, how hard it becomes to revert the obfuscated code back to the original form. That's resilience. Now you see another example of renaming all the variables and removing comments. This is a perfect example of an obfuscation that is 100% resilient. Why? Because you can never get the original names, so you can never go back to the previous form. And of course, the comments, you cannot ever retrieve them. And this is the result of applying another obfuscation, string splitting, to the previous form. At first glance, you can see that it's more potent, it's harder to read, but is it more resilient? If you spend a couple of seconds, you can see that it's not that hard to reverse it back to the previous form. In fact, but before that, let's talk about what we can do automatically to reverse obfuscation to a previous form. The first technique is using static code analysis. A static code analyzer parses the code. It then usually transforms it to fulfill a purpose, like for instance, make the code simpler, usually with the goal of making the code faster. But this is also something that is compatible with the goal of reverse engineering that code. So some examples of simplifications that can be made to the code. You have constant propagation, which finds the constant and replaces the constants throughout the code with its value, and constant folding, which picks up expressions and solve them statically. But the most importantly, also you can use static code analysis to remove that code that can be detected statically. Not every dead code can be detected that way. But most importantly, this is an automatic method. So what is the effort needed to apply this? It's none. You just have to press enter a comma. Here you can see the previous command, the previous example, sorry. And you can see the result of applying the Google Closure compiler to that code. This is a static code analyzer. And you can see that it can really simplify the code. And in fact, the result is very similar to the previous form of the code. I can even show you the original form of the code, and you can see that it's not that different. Apart from the variable names that you cannot get them back, the rest of the stuff is pretty much the same. Okay, so we can say that string splitting in this case is not that resilient, because you can get back to the previous form using static code analysis. You can also use dynamic code analysis, contrary to static code analysis, which never executes the code. Dynamic code analysis needs to execute the code. That can be useful to retrieve values of some expressions present in the code, instead of understanding what a big expression calculates. You can just run the code and see what is the result that gets stored in some variable. It also helps you get the control flow graph of the code. This is a representation of the lines of code that were executed during the runtime. So dynamic code analysis can be really useful to reverse obfuscation, but you must understand that it will only get you one instance of the execution of that code. If you run the code again, you might get a different path, execution path. So, of course, there's another advantage, which that code will never be in the control flow graph, because that code, by definition, is not executed. But this technique is no good for automatic reversal of the obfuscation because it cannot guarantee you that you will get all the code that will ever be executed by the program. But it's very useful to get the knowledge for doing manual reverse engineering because you can understand bits and pieces of the code and then manually try to simplify the original source code. But of course, you run the risk of making errors. Another metric is stealthiness. How hard it is to spot what modifications were made by a certain obfuscation. To make an obfuscation more stealthy, you should avoid using telltale indicators such as the eval function, an escape, or large chunks of meaningless text, which usually indicate that someone is trying to hide something. Another very important metric is the execution cost, or the impact on performance or loading times. Usually you measure this in terms of runs per second. Sometimes it makes more sense to use frames per second because in games that's ultimately it's what counts. Although you may think that obfuscation usually does not improve the performance of a program, you're right. But not necessarily it will have an impact on performance. For instance, the renaming obfuscation, it exchanged the name of the variables and function. It has zero impact on execution cost. And usually you can always get a mix of obfuscation transformations that will not have a significant impact on the code. Just have to understand the nature of your code and what you can do to it and not hurt performance. Also, it's very relevant where the code is being executed. If the code is being executed on a smartphone, you have to be a little bit more conservative than when executing the code on a browser. The impact on loading times, which is the time before the code starts executing. Mostly this is associated with the size of the code. Obfuscation can have an impact on this. It can grow the code. But again, some transformations do not have a negative impact on the size of the code. In fact, the same example applies here. Renaming the variables does not grow the size of the files. In fact, the renaming is used by minifiers, so usually it replaces long, meaningful names with short names, and thus reducing the overall size of the files. Sorry, that was not shown. Finally, the maintainability of the code, which is the effect. It's usually can be seen as the inverse of the potency, but only after using automated ways of reversing the code. Because only then you are seeing the real potency of the obfuscation. In a way, this is associated with the resilience, because the more resilient is an obfuscation, the less you can revert back automatically. This is a very important concept because the lower maintainability you can get with the code, the more you mitigate the risk of someone being motivated to steal your code and reuse it. Now let's enter the fun part of the presentation. And let's start by an example that is one of the most misconceptions, which is there are lots of people that do not understand the difference between compressing or minifying the code and obfuscating the code. This code is a portion of an MD5 function. It's just an example. And here you can see a compressed version of that code. Well, we can see that it's definitely more potent. It's harder to read, to understand. But is it more resilient? If we look closer, we can see that it uses an eval. So whenever you see an eval, what do you think? Let's see what it's underneath it. So by using a simple trick, removing the eval, you can see the underlying code. And in fact, by comparing with the original source code, you can see that it's pretty much the same. So what at first glance seemed like a very potent obfuscation is in fact a very, very not potent. So the real potency of this obfuscation is this one. It's the one you get from reversing it back. So this is a very non-resilient obfuscation. And in fact, well, the purpose of compressors and minifiers is not to protect the code at all. Their sole purpose is to reduce the file size and to make the code run faster. Another example, which I like very much, is non-alphanumeric obfuscation. It was first proposed by Asegawa, and it's an encoding method which strictly uses non-alphanumeric symbols. Let's look at one example. You consider this code, alert 1, and this is the non-alphanumeric obfuscated version of that code. So what do you think? Is it potent? Now, how is this possible? I'm sure some of you already know it. Let me go through it because perhaps some do not know. This is possible because JavaScript has something that is called type coercion, and due also to browser quirks. You must first understand that we can pretty much get any alphanumeric character indirectly. For instance, if you use a plus in front of an empty array, you'll get a 0. And if you negate that, and you do again type coercion to integer, you get 1. So anyone can tell me how I get 2? No? Just add it. Okay, so using this you can get pretty much any number. Now you can see how I can convert a number that's on a string to a number. And the opposite, which is by adding an empty string, I can convert a number to a string. Now, how do I get letters? I can get it this way. I can use type coercion to try to convert the character to integer, but because this is not a number, I will get not a number. And by adding an empty string, I get not a number inside a string. And by using the array access to the first character, I will get an uppercase N. But I still have alphanumerics here, so how can I proceed? I can start by replacing the 0 with this one, okay? And then I have to get rid of that A. So how can I get an A? Someone could answer if I study hard, but I can do this. I can negate an empty array, and I would get false. Then I had an empty string, and I had false inside the string. Now I use the same method as before to get the name. Replace it back, and ultimately I will get an uppercase N. Okay? So if I use this method, I can, for instance, use run the alert one, just obfuscating the first letter using this technique. Okay? And this will pop up an alert. But, okay, I can pretty much obtain any letter I want, either using these methods or using the character code. But you saw that I used an eval. An eval uses letters. So how can I get rid of those letters? Well, eval is not the only way to do eval. In fact, you have 4 or 5 methods more. For instance, you have these ones, but you have this one, which is more interesting because it uses subscript notation, and it has strings, and I can convert that to non-alphanumeric, as I explained before. So eventually, this will result in this garbage you see here. And you can see it starts by an empty array, and next you would see sort, converted to non-alphanumeric, and so on and so on. But, well, obviously, it's one of the most potent obfuscations. It's 0% stealthy because if you can see it, you know that someone is trying to hide something. It has kind of a high execution cost because just using eval is a little bit slower. But the worst problem is the file size. Can you imagine like jQuery converted to non-alphanumeric? Well, another problem is that it does not work in all browsers. Some older browsers are not able to support this. But what about resilience? Is it resilient? What do you think? Well, not much, because you can use pretty much the same technique to revert back to the original form. But it's good for bypassing filters. I'm giving you a couple of ideas here to test your walls. Okay, so let's move to another example. Dead code injection is a very natural way of inserting confusion in one code. And because dead code is never executed, it does not have an impact on execution cost. So this is a bit of benchmark JS. And here you have the same code with dead code injected. And also rename block. So can you spot where is the dead code? It takes some time. It is here. Now, would static code analyzers remove this code? Well, usually static code analyzers remove that code, but not this example, because it uses opaque predicates. What is that? Opaque predicates are expressions, logical expressions, which you cannot easily tell if it's going to be false or true unless you run the code. So a static code analyzer does never run the code, so it cannot remove this code. So you cannot automatically remove this type of dead code. Also, to make it a little bit more stealthy, the predicates were inserted to look similar to other predicates present in the original source code. They were randomly injected, and the control flow of the program was a little bit increased, so definitely it is a more potent obfuscated version of the code. There are dummy statements on that example that were created out of code existing in the original code. And so it also adds some confusion, but mostly it adds some stealthiness to the obfuscation. Now, up to now, we have seen examples that use no more than 2 or 3 obfuscation transformations at once. Let's go back to the original example and see what happens when we mix a larger number of obfuscation transformations together. Now, I will give you 1 second to look at this and memorize it all. You're done? Okay, this is every obfuscated version of the previous code. Now, intentionally, I didn't use encoding in this obfuscation. And the purpose was to let you see how these transformations combine, what is the look of these transformations. But let me tell you that not all encoding transformations are easily reversible. For instance, you can install additional checks to the code that will encode it using information of the environment, but not from the code. For instance, the domain the code is running, you can use it to develop domain log. So whenever the code is running on a different domain, the code will not be decoded properly. Okay, so it's not easily reversible unless you know what is the original domain. Here you can see the result of applying static code analysis to the previous form using Google Closure Compiler. And as you can see, it didn't help much. And this is because the transformations used are added a good degree of resilience to the code. So someone would need to spend a lot of time trying to simplify this by hand, like you did for Google Maps. Although Google Maps, as far as I know, uses mostly minification and not real obfuscation, confusion, and resilience. And in conclusion, people often judge obfuscation based on the potency, the apparent potency of the code, when in fact it's what matters the most is the resilience. Because with the testing the resilience, we'll give you the actual potency of the code. And of course, by looking at simple examples with one or two transformations, by comparing them, you can perhaps easily tell which one is more resilient than the other. But when you compare different obfuscated versions using a lot of different transformations side by side, how can you tell which one is more resilient than the other? I mean, it's not trivial to do that. So that is the job for commercial JavaScript obfuscations. So you have to do some analysis of what they provide, and then you have to choose one and trust they are doing a good job in choosing the right set of transformations to protect your code. So obfuscation, finally, can be very effective to prevent code theft and reuse. This is very important because most of the time people look at obfuscation as, does it stop people from getting your secret? Well, eventually it does not. If someone spends enough time, eventually it will get the secret. But that is not the most important concept around obfuscation. The most important is that you can lower the maintainability of the code so much that someone will want to like write that code from scratch instead of stealing your code. So this is it. I look forward for your questions.
Okay, thank you very much. Questions, please. If you have evolving JavaScript, so you have multiple versions, for instance, in the recurrent month, does it impact your resilience if you have the same transformation being applied to small differences in code?
Well, if I understood correctly, if you apply the same techniques, does the attacker have more information over time that is able to deduce what is being made to the code and therefore reverse it? Well, yes, but one aspect of obfuscation is that some transformations are random. If you do it many times, you always get different code. Okay, so the real question is, do you is it easy to understand that different versions of applying the same transformations are using the same transformation? Is it easy? Or does the attacker think that they are completely different transformations being used? That's the real question. Because if you do an analysis, knowing all the information, knowing all what is the original source code, what transformations were used, you are really having information that most of the time the attacker does not have at all. If you have the original source code, oh, I know where this function begins. All right, but if you look at completely a code with which you are unfamiliar, can you understand the code? How much time do you need to reverse it back to something that is useful for you?
The second question, that if you have static code, do you see use case where you say the same static code is for each version going out to a customer, different techniques being applied, or is always only one transformation then be sent out to all the clients?
Usually a set of transformations. Actually, this is associated with something I said in the last slide, which is usually the clients do not choose the set of transformations. They can do it, but it's usually not the best option.
Okay, but I mean,
usually the obfuscator.
You have a set of transformations, but you have two web browsers, two clients visiting the same page. Will you deliver them always the same end product, or will you have the randomness generating?
No, I understand, sorry. Well, you can do both. You can deliver the same, or you can deliver a new one, each request. It's just a matter of generating more obfuscated versions of the original source code, which by being a random process, by having randomness, you will get different forms, different obfuscated forms. But if you use the same transformations, you will have the same degree of potency and resilience.
Okay. Any questions? No? I happen to have one. One of the ways you look for vulnerabilities on the code is by looking at the source code and by understanding how the source code works. How can obfuscating JavaScript can be a barrier to this kind of analysis?
Well, you can look at it using two ways. One view is that open source code, it's not easier, it's not necessarily easier to spot vulnerabilities. Because over time, attackers, didn't have problems finding vulnerabilities in closed source code, right?
Yeah.
But you can argue, that's the second view, you can argue that it's tougher to find vulnerabilities in more closed code.
Yeah.
So the real question is how resilient is the closed code? How resilient is the obfuscated code? Because if you have something that is close to 0% resilient, now that's almost equivalent to using the original source code. But if you use instead an obfuscation that is close to 100% resilient, then it's much harder to find vulnerabilities using the obfuscated version, of course.
Okay. The question is, imagine for instance that someone produces a malicious script and obfuscates it and sends it to the client, or puts it some way inside a web application. The question is, how do you know, how can you be aware that this script, which apparently it's a good script, it is being produced by someone which you trust, is now a malicious script, but it's obfuscated? Is there any way for having some kind of cross-checking, like you have a mechanism for ensuring that the guy who obfuscated this JavaScript is the right owner of the application and which is the right version of the JavaScript running at the end user side? Is there some mechanism like this?
Well, I believe that you can use solutions like JSAT for doing that. Obfuscation does not really care about what is the purpose of the code.
So it's something which is out of scope.
Yeah. It's out of scope of obfuscation, but there are other solutions that can detect if some property is being accessed. Some antivirus, if they find an eval on JavaScript, they will pop up an alert. So, do you think that anything that uses eval is malicious?
Not necessarily.
Not necessarily.
Okay. Someone else? No? So thank you very much.